Okay, 9-1 polar coordinates. So as we get into graphing polar coordinates, we're now going to work on a different coordinate system, things that are going to go in a circular motion. So until now, everything that you've graphed has been on the coordinate plane, which is rectangular, and you've had the points x, y. Oh, there it is, and points have been in the form x, y. However, the Earth, being spherical, makes sense that there would be applications that require a different method of graphing, such as when air traffic controllers locate aircraft using distance and angles. This is known as a polar coordinate system. So again, this is going to be based on circular movement, rotating angles and distances away from the center of a circle, and that's going to be instead of the rectangular system. So in a polar coordinate system, the origin that we typically think of in the rectangular system is still a fixed point O, but in the polar coordinate system we call it the pole. And then we have what's called the polar axis, and this is an initial ray. Okay, so it has if you look over here to the right, it has a starting point, and it goes in the direction of the positive x-axis, but it is a ray, and it usually does go from horizontal, and it's to the right. The ones that we'll be working with will do just that. So the location of a point P, and again, it is a point, is in the form r theta instead of xy. So r is now going to be the distance from the pole to the point, and theta is the directed angle from the polar axis. So just like our direction angles that we talked about in chapter 8. So as we look at the point over here, the picture over here, we have the pole, the polar axis, and we can see that r is this value right here. It's the distance. But again, what we're really graphing, keep in mind, is a point. It's a location in space, and it's r theta. So theta is the angle of rotation from the polar axis, and r is the distance from the pole. Okay, so let's talk about how we graph these. So to graph a point given in polar coordinates, a positive value of theta, just like always, is going to indicate a counterclockwise rotation. From the polar axis, and a negative value is going to indicate a clockwise rotation. So this is what we've looked at before. This should be totally familiar. So now let's talk about r. A positive value of r indicates that the point P will lie on the terminal side of theta. So it will be directly on that ending terminal side. But a negative value of r indicates that P would lie on the ray opposite the terminal side of theta. So if you think back to when we were doing vectors, if we had a vector with a magnitude of 3 going in this direction, well, if we have a magnitude of -3, it's going to be a ray just as long in the opposite direction, or a vector, and this would be -3. So if we think about our polar coordinates, and this was the pole, and this was the polar axis, instead of going out 3 on the terminal side of theta, we would end up going the other direction and plotting a point. So let's look at some examples. We're going to graph point A. So A is the point 2, 45 degrees. So 2 is my r value, 45 is my theta value. And so as I look at, or I think about the pole, which is like my origin in rectangular coordinates, and the polar axis, like the positive x-axis, what I'm going to do is I'm going to think about rotating 45 degrees, which would be like that. Because it's positive, I'm going to go counterclockwise, just like always. And then a distance of 2, if we think about concentric circles, is going, each circle, let's think of as having a radius of 1 unit. So if I'm going to plot the point 245, I'm going to go from the pole out 2 units on that circle and on the terminal side of what would be that angle. And this would be the point A. So again, even though it's r theta, I tend to rotate first and then go out however many units in the positive or negative direction and plot your point. Okay, let's look at letter B. So for letter B, let's draw the pole and the polar axis. This is our coordinate system, and so we are going to rotate 2 pi over 3. So again, this is r theta. So we're going to rotate theta 2 pi over 3, which would be over here in the second quadrant. So theta would be 2 pi over 3. Oh. And then if I'm going to do a negative 1.5, we're going to picture those concentric circles. Each radius is 1. And instead of going out on the terminal side, where we have 2 pi over 3, we would go in the opposite direction, 1.5. And this would be my point right in between 1 and 2. It is in the opposite direction of the terminal side. So there's point B. So that's basically how we graph polar coordinates based on r and theta. Let's practice some more examples. Okay, so to graph points on a polar grid, you're going to follow the same procedure as you did for the polar coordinates like we just did, only now the grid is provided, and honestly, it's going to be a lot easier. So graph each point on a polar grid. So as we look at this, the first one is in radians, and in B we have degrees. So you can do it in both, and then you'll look at each of the circles as they go out. Each radius is up 1 unit. So let's graph 4 pi over 3. So this is r theta. The first thing I'm going to do is rotate to 4 pi over 3, which is over here. Go all the way down into what would be like the third quadrant. So I'm going to be over here. And then I'm going to go out 3 units. 1, 2, 3. And there's point P. In what we would think of if we were to overlay the XY coordinate system on here, if we overlay that on top of this, point P would be considered to be in the third quadrant. Okay. Then B, point Q. We have negative 3.5 and 150 degrees. So I'm going to rotate to 150 degrees, which is out here. And then instead of going out 1, 2, 3.5 right there, I'm actually going to go in the other direction, which would put me at the 330 degree, 1, 2, 3.5 right here. So again, the 150 had a reference angle of 30 with the 180 degrees. And so when I go the opposite direction, I still want a reference angle with the x-axis of 30 degrees. So this would be my point Q. I rotated 150 degrees, but instead of going out on the terminal side, I went in the opposite direction, negative 3.5 units out. Okay, so that's doing 1 point. Now, just like an angle on the unit circle has an infinite number of coterminal angles, if you remember when we did coterminal angles, we could list infinitely many angles because of the fact that it goes around and around and around. The same is going to be true with identifying polar coordinates. So what this means is that we could take this 1 point r theta and describe it several different ways in degrees and radians. We could take r and then theta, add or subtract 360, and then r, add or subtract 2 pi to theta, and be in the same location. So as we look at example 3, we have point T. Find 4 different pairs of polar coordinates that name point T, and here's what's important. You have to be between negative 360 and 360 for theta. So let's look at point T. The first most obvious way to name this would be to do your rotation. It's 135 degrees out. There's my theta. And if that's the terminal side, I go out 1, 2, 3, 4. So for 135 degrees would be probably the most obvious way to label T. Now we need to find 3 other ways to label T. One rule of thumb I like to use that helps you stay between negative 360 and 360 is to use 2 positive r's and 2 negative r's. The idea is they don't want you to just keep subtracting 360 or adding 360. So as we think about the next value, if I have a positive 4. That means I want to be right where T is once I rotate. Well, what I can do is I can take that 135 and subtract 360 degrees. And that is going to put me at 4 and negative 225 degrees. So that's another way to get to that point. Rotate negative 225 degrees and then go out 4 units. Now, negative 4s. To get the negative 4s, what would have to happen is I would need to land 1, 2, 3, 4. I would need to land out here at first, and then the negative is going to take me back to that point T. So one point that I would have would be negative 4 and 315 degrees. Or my reference angle here is 45 degrees, so that would be a negative 45 degree rotation. Now there's several ways to label these points, but there are 4 ways that you can label point T. Okay, that's working in degrees. Now let's see how we do it with radians. So find 3 additional pairs of polar coordinates that name the given point if we have to stay between negative 2 pi and 2 pi. So I have, let's take a look at where this would be. There's my pole and my polar axis. I'm going to give myself 2 concentric circles. So pi over 6, if we rotate out, that's about 30 degrees right there. And so 2 pi over 6 would be right here. So I want one more with a positive 2, and I'm going to do 2 with a negative 2. Okay, so another way to do that, to stay right there, I'm going to take that pi over 6 and subtract 1 whole revolution, which would be 12 pi's over 6. So positive 2 and negative 11 pi over 6 is another way to get to that point. Now, to use the negative 2, if I want a negative 2, that means I've got to land out here and then reflect back. So what would land me out here would also have to have a reference angle of pi over 6. Well, that would be 7 pi over 6. Essentially, the math that I'm doing is taking pi over 6 and adding 6 pi's over 6, 180 degrees or pi radians. And then I get my negative 2, 7 pi over 6. The other way to do that would rotate this direction, so negative 2, and if I would take that pi over 6, and I'm going to subtract 180, 6 pi over 6, that fourth point would be negative 2 and negative 5 pi over 6. So don't try to memorize, always add, always subtract, 360, 180. Honestly, I think the easiest way to do this is to kind of sketch out what you have. Think about the different ways to get there, adding and subtracting 360, 180. Use the big picture, look at the concept, look at the visual of what's going on. Okay. The next thing we're going to do is graph some very basic polar equations. So there are 2 types, again, these are basic, 2 types of basic graphs in the polar coordinate system. The first is equations of the type r equals k. In this case, k is going to be my number. Maybe r equals 3, r equals 2. Now r will always be positive in this case when we graph. We want to represent what this graph looks like is a representation of right here, all points that are k units from the pole. And if you think about what that is, it will be a graph of a circle, k units from the pole, centered at the origin or the pole. So if I go down here now and I look at example 4, letter A, r equaling 2 is going to be a circle with a radius of 2. All the points that are 2 units away from the pole. Okay, the other type of graph is going to be equations of the type theta equals k. And again, k is a number, and this is going to be our degrees or our radians. theta equals 135 degrees, theta equals 3 pi over 4 radians. It is all the points on that line that make an angle of K with the positive polar axis. So what does that look like? It is, first of all, a line. That's really important. It goes on in both directions. So it is a line that does what? It makes an angle of K, whatever K is, with the positive polar axis. So if we go to example B, it says theta equals pi over 6. This is going to be a line where all the points, or it makes an angle of pi over 6 with the positive polar axis. And there's the graph of theta equaling pi over 6. Pretty basic. Okay, the last thing we're going to look at is the polar distance formula. Just like we have a distance formula for our rectangular coordinates where we're trying to find the difference or the distance between 2 points on the rectangular coordinate system, this is where we want to find the distance between 2 sets of polar coordinates. And we're going to jump right in with an example on this. But first of all, the polar distance formula says this. If I have 2 points where P1 equals R1 theta 1 and P2 equals R2 theta 2, the distance between them is given by this. And you will be given this formula. It is the square root of R1 squared plus R2 squared minus 2 times R1 times R2 times the cosine of theta 2 minus theta 1. And that is going to be an important combination. Okay, so example 5 says this. This is a neat example. An air traffic controller is tracking 2 airplanes flying at the same altitude, so on the same plane. The coordinates of the planes are A, which is at 5, 310. So I'm going to go out here and graph this. 310 would be about right here. There's A, 5, 310 degrees. And then there's plane B, which is at 6, 345 degrees. So that would be right about here. 6, 345. So it says sketch a graph of this situation, and there it is. Okay, question B says, or problem B says, if regulations prohibit airplanes from passing within 3 miles of each other, are they in violation? And explain. Well, we're simply going to do the distance formula to know how close the planes are. So we're going to take the distance of AB and just plug into that formula. So A is my R1 theta 1, and B is my R2 theta 2. And from here, we're going to plug into our formula. So I'm going to get R1 squared, which is 5 squared, plus R2 squared, which is 6 squared, minus 2 times R1, which is 5, times R2, which is 6, times the cosine of theta 2, which is 345, minus 310, theta 1. Okay, you can go right to the calculator. I'm going to simplify this with a little mental math first. That's less that we would have to plug in and less room for errors punching in the numbers. So I'm going to do 25 plus 36 minus 60 times the cosine of 35 degrees. So make sure that your calculator's in degree mode. You can now make this, if you want, 61 minus 60 times the cosine of 35. A lot less room for error plugging that in. And when you go to your calculator and you evaluate this, your decimal value is about 3.44 miles. So if they're not allowed to be within 3 miles of each other, they are not in violation. And that's a good example of how we can use that polar distance formula. Okay, so this takes us up through 9.1, polar coordinates, and some graphing and the distance formula.